Hello everyone, it is an honor for me to give a speech today. Our work is focused on the big issue of storage management for multi-tenants in cloud object storage, and the prototype system is implemented based on the OpenStack Swift platform. I will first introduce the background and motivation part, which contains the studied tests for motivation and summarize the goals and challenges, and then I will explain the design. After that, I will show the effect that our design can achieve. Finally, the conclusion helps to review the whole speech. Due to the explosive growth of data, cloud object storage becomes more and more popular due to its high availability, flexibility, and simple data management. Specifically, the flat address space of object storage avoids the complicated directory overhead in the file system. Besides, the RESTful API based on HTTP protocol simplifies the interaction between users and the storage. In addition, storage virtualization technology improves resource utilization. Therefore, more and more tenants choose to deploy their applications on the object storage cloud. However, the differences between workloads on a shared storage cause problems. Typically, the workloads are likely to have different access characteristics, resulting in different performance requirements. For example, social networking applications generate frequent read requests, and low latency is needed to support a highly responsive user experience. On the contrary, enterprise backup applications consist mainly of write requests, which can tolerate higher latency but needs consistently high throughput. However, unfortunately, many existing cloud object storage systems use a monolithic configuration to serve different workloads, limiting their performance to the same service level. Therefore, the gap between the diverse workloads and the fixed storage leads to poor performance and low efficiency. Regarding the gap between the workloads and the storage, OpenStack Swift, as a mainstream cloud object storage system, has made its own efforts. Since the Juno version released in 2014, a storage policy mechanism has been developed. Let's start with a basic understanding of OpenStack Swift. The Swift system is a two-tier architecture. The front-end access layer is mainly responsible for the authentication and request forwarding, while the backend storage layer is mainly responsible for managing storage devices and data. The key role in the proxy server of the access tier is the object ring, which is used to determine where data of an object should reside in the cluster. Each storage node is logically divided into multiple storage devices, while the partition is used as the forwarding unit, and the partition contains a group of storage devices from different storage nodes. The object ring includes two stages of mapping when forwarding, the request to partitions and the partition to storage devices. Typically, the first n bits of the MD5 hash value of the request path are used to index the nth power of two partitions on the ring. The n value means the partition power. These partitions are then assigned to multiple storage devices on the storage nodes, and the number of the storage devices is indicated by the replica counts m. Swift's storage policy is realized through the creation of a specific object ring. Each storage policy corresponds to a separate ring, and this ring can be configured with different values of n and m. That is, the number of partitions on the ring and the number of replicas of each object can be customized. Therefore, different reliability requirements can be met through different rings, and the different performance requirements can even be met through different storage media. Next, we further understand the advantages and the limitations of the storage policy mechanism by tests. First, we illustrate the advantages by comparing with the monolithic configuration. As shown in the figure, under a monolithic configuration, that is, when all workloads share the same policy, the The performance of workloads with different access characteristics is limited to similar throughput. However, when different policies are separately configured for the workloads, the performance is greatly improved. The throughput is increased by up to 8.5 times, and the latency is reduced by up to 33%. The performance improvement comes from two reasons. First, configuring separate policies allows the workloads to experience isolated forwarding paths. Secondly, separate policies can alleviate the resource competition. Based on the separate policies for different workloads, we perform stress tests on each workload by varying the request concurrency. The concurrency is controlled by the number of workers. For each workload, the same storage policy is adopted for scenarios with different request concurrency. From the experimental results, the performance of the workloads show the similar trend. That is, as the request concurrency increases, the throughput first increases and then reaches saturation, whereas the latency first increases slowly and then increases sharply after the throughput saturation. This indicates that the performance of intensive workloads still has room for improvement. Given that the complete storage path includes not only the request forwarding but also the request processing, the existing policy mechanism only covering the forwarding path is insufficient to guarantee the end-to-end performance. Therefore, we envision an enhanced storage policy mechanism to cover the entire storage path. During the request processing, the policies provide specific performance optimizations based on the characteristics of different workloads. What's more, the mechanism should be dynamic and flexible to adapt to the workload changes. To achieve these goals, four main challenges need to be addressed. The first one is how to control the request processing path, and the second one is the workload classification and requirement determination. The third challenge is the request identification, which comes from the fact that the source information of request is unknown to the storage layer. And the last challenge is how to adjust the policy at runtime. Here is the overall system architecture of our work, MAS. The architecture is divided into the control plane and the data plane. Among them, there are three main abstract components: controller, monitor, and substore. The controller part includes a central controller and a group of microcontrollers. The central controller is responsible for coordinating the formulation of policies. For each policy, a microcontroller is responsible for policy deployment. The monitor components include a system monitor and workload monitors. The system monitor collects some performance indicators of each node, such as I/O weight, CPU usage, and memory usage. The workload monitor counts the read and write requests of the workload. The information is transmitted to the central controller for workload classification and policy decision. According to the access characteristics, the workloads are classified into three types: read-dominated, write-dominated, and read-write mixed. In the data plane, we use the method cross-layer tagging to enable workload identification. Specifically, before the request is forwarded, the original tenant information is tagged in the extended metadata. The request can thus be identified by obtaining the corresponding tagging information. At the storage layer, the implementation scope of each policy is abstracted as a substore, and the optimizations of request processing are performed in the substore. The life cycle of a workload-specific policy includes four important stages. The first one is policy preparation. The central controller classified a target workload based on the information from the workload monitor and selects a set of storage devices to form a substore for the workload. Then comes the policy formulation stage. By controlling the creation of a specific ring, the central controller is able to connect the workload with the substore. The policy is in a triple format, including the tenant information of the workload, the specific ring index, and the optimized method to perform in the substore. Then, the central controller creates a dedicated microcontroller and hands over the policy. The microcontroller carries out the third stage, policy deployment. Necessary information is delivered to middlewares on the proxy server and the storage nodes for request tagging and identification. The last stage is policy execution, which means the policy taking effect on the data plane. The requests are not only forwarded by the specific rings but also processed with performance optimizations. In the backend storage layer, we achieve two-level processing optimizations. The substore level policy represents performance optimizations for different workloads depending on their performance requirements. For read-dominated workloads, we use cache policy to reduce the latency. For write-dominated workloads, we use batch policy to increase the throughput. As for read-write mixed workloads, we use merge policy to comprehensively improve the performance. The policy mechanism we proposed is programmable, so the policies are extensible. On the other hand, a storage node manages multiple storage devices that belong to different substores. That is, requests of different workloads are processed on the shared storage node. Therefore, at the storage node level, we coordinate requests of multiple workloads by priority control to promote the system efficiency. Generally, requests of different workloads are arranged in different queues. The more read requests the workload contains, the higher priority the queue owns. In particular, for the replica mechanism, there are two types of write: the write of the first replica and the write of the non-first replica. The latter owns lower priority because it means there exists a successful replica write already. We thus extract write requests of the non-first replica to form a separate queue with the lowest priority. Our policy mechanism is dynamic to deal with possible workload changes during runtime. We divide workload changes into the external and internal. The external workload changes occur as the demands of tenants change. Consider a scenario where the workload demand from one tenant is spiking while the demand from another tenant that shares the same object storage is dipping. In this case, if the policies remain the same, two problems arise. First, the static policies would result in the improper allocation of system resources. The tenant with the increased demand face insufficient resources, while that one with the reduced demand has idle resources. Second, implementing policies introduces the overhead, and the overhead can be accepted for greater performance gains. However, when the tenant demands decrease, the performance gains are not enough to trade off the overhead of the policy. The internal workload changes refer to the fluctuations of the access characteristics of the workload. Similarly, it still results in the improper allocation of resources and poor workload performance. All workload changes need to be judged for validity. Once valid, adjustments are made through the insertion and deletion of policies. Next, we use experiments to show the effects that mass can achieve. The cluster we use for the experiments includes 2 proxy nodes and 5 storage nodes, and the other 3 machines are used to generate workloads. We resort to synthetic workloads and replace of real traces, as shown in the table and figure below. There are 2 storage configurations for comparison. One is default, which relies on the existing policies of Swift, and the other is Crystal, that workload-specific policies are provided manually but cannot be dynamically adjusted. First, let's look at the ability to use policies to handle diverse workloads. Workloads A, B, and C come from 3 tenants and share storage. Under the default configuration, requests of different workloads are mapped to separate sets of storage devices through different rings. Under the Crystal configuration, different policies are manually specified based on access characteristics. Under the mass configuration, policies are assigned to each workload at both the substore level and the storage node level. From the experimental results, it can be seen that compared with the existing storage policies, the overall system throughput is increased by 154.3% and latency is decreased by 67.8%. For each workload, the performance is optimized greatly. Next, let's see the scenario where mass handles external workload changes. We use workloads A and C as 2 coexisting workloads for a 3-stage test. The first stage acts as the baseline. In the second stage, the demand of workload A is increased and the demand of workload C is reduced. The third stage takes the opposite actions of the second stage. From the experimental results, compared with the default configuration, mass can better react to external workload changes. For workloads A and C, the latency and the throughput is promoted respectively. Since the real-world workloads are often accompanied by fluctuations in characteristics, we use the replace of real traces to show how mass handles internal workload changes. It can be seen that mass can perform better than the other 2 configurations, which shows that the enhanced storage policies are more effective and the advantages of dynamic mechanism. Starting from the existing storage policy mechanism, we found that when the requests become intensive, which is commonplace today, the policies cannot guarantee satisfying performance. Besides, the policy mechanism lacks flexibility, which makes it unable to cope with possible workload changes. Therefore, we propose mass to provide enhanced policies. In addition to controlling the forwarding path, it also controls the processing path of the request and provides workload-aware performance optimizations based on the access characteristics. Moreover, by separating the policy control from the data plane, the policy mechanism becomes flexible to enable the dynamic adjustment of policies during runtime. Finally, compared with the existing storage policy mechanism, mass achieves better workload performance and higher system efficiency. That's all for my speech. Thanks for listening.